Hello, viewers. In today's session, we are going to discuss an important problem from limits. And in this session, we are going to discuss the limits of this form, that is 1 raised to infinity, with the help of this example. Right. So here we are taking this example as an illustration to explain how to calculate the limits of this form, that is 1 raised to infinity. So let us start. So viewers, we have already discussed these kind of limits in our earlier videos, and we have also discussed in detail how to evaluate limits of this form. But in those cases, the functions were mostly trigonometric functions, right? So here we are going to discuss this limit where we have algebraic functions, right? So let us first call this limit as L, and here we have limit x tends to infinity, and the function is given as x plus 7 divided by x plus 1 raised to x plus 2. So let us first take this function as p1x, right? So we have the function p1x is equal to x plus 7 over x plus 1, and let us call this function as p2x. So this is x plus 2. So now this limit, it takes this form, that is limit x tends to infinity, and here we have p1x raised to p2x, right? So now let us first calculate this limit, that is the limit x tends to infinity, and the function is p1x, and let us call this limit as L1, right? So we are separately calculating the limits of these two functions when x approaches to infinity. So here we have limit x tends to infinity, p1x is x plus 7 over x plus 1, right? And we know that how to calculate the limits of rational functions. When x approaches to infinity, we divide the numerator and denominator by x. So we have x plus 7 over x, and here we have x plus 1 over x. So now we can write limit x tends to infinity, and here we can write this expression as 1 plus 7 over x, and here we can write 1 plus 1 over x. Now see, when x approaches to infinity, then 1 over x, it tends to 0, right? So this term and this term, both these terms tends to 0 when x tends to infinity. So we have simply 1 plus 0, and here also we have 1 plus 0, that is 1 over 1, that is equal to 1. So from this discussion, we have reached the conclusion that the value of this limit is equal to 1. It implies that L1 is equal to 1. So now let us calculate the value of L2, that is limit x tends to infinity, and here we have the function p2x. So this is the limit x tends to infinity, p2x is x plus 2, right? So now this is a linear function. So when x approaches to infinity, then x plus 2 also tends to infinity, right? So this limit, it tends to infinity, right? So from the values of L1 and L2, L1 has the value 1, and L2 approaches to infinity, right? So this limit now takes the form that is 1 raised to infinity, because limit extends to infinity, p1x is 1, and limit extends to infinity, p2x, it tends to infinity. So the overall limit, it tends to this form, that is this L, it tends to a 1 raised to infinity. So here from this discussion we have established that this limit is of this form, that is 1 raised to infinity. So whenever we come across with these type of forms, then the value of the limit can be calculated by this result, that is e raised to a limit, and here we have x tends to infinity, and then we write here the function p2x multiplied with p1x minus 1, right? So whenever we have a limit of this form, that is limit x tends to a, p1x raised to p2x, and the limit x tends to a, p1x is equal to 1, that is L1 is equal to 1, but L2, that is limit x tends to a, p2x tends to infinity, then in these type of limits we can directly find out the value of the limit by using this result, right? So the value of the limit L is equal to e raised to limit x tends to infinity, p2x multiplied with p1x minus 1. So in general we can also write e raised to a limit x tends to a, then we have here p2x multiplied with p1x minus 1, and here our a is infinity, right? So let us now substitute the values of p1x and p2x in this expression. So now we can simply write L is equal to e raised to limit x tends to infinity. Here e is the famous exponential number. P2x is x plus 2, and here p1x is x plus 7 over x plus 1, and here we have minus 1, right? So now let us first simplify this expression. So we have limit x tends to infinity. Here we'll keep x plus 2 as such, and we'll first simplify this expression. So we have x plus 7 minus x, and here we have minus 1, and here we have simply x plus 1. Now this x and this x get cancelled, and we are left with limit x tends to infinity, and here 7 minus 1 is 6. So we can now write this 6, that is 7 minus 1, 6, in front of this limit notation, because this is a constant, and we have here simply x plus 2 over x plus 1, right? So now we can write e raised to 6, and here we have limit x tends to infinity, and here we have a rational expression, right? So in the numerator we have a polynomial, that is a linear function, and in the denominator also we have another polynomial, which is another that is a linear function, right? So dividing the numerator and the denominator by x, we have x plus 2 over x, and here we have x plus 1 over x. So now we can write e raised to 6, and here we have limit x tends to infinity, and we can write x plus 2 over x as 1 plus 2 over x, and here we can write 1 plus 1 over x. Now as we have just discussed, when x tends to infinity, 1 over x tends to 0. So now this term reduces to 0, and this term also reduces to 0. So now we have the value of L as e raised to 6, and here we have 1 plus 0, and in the denominator we have 1 plus 0. So this is simply e raised to 6 times 1 over 1, that is e raised to 6, right? So the value of this limit L is equal to e raised to 6, which is a finite quantity. So this is how by making use of this important result, we can evaluate the values of these type of limits, or limits of the form 1 raised to infinity. But here remember, the limit of the function p1x must tend to 1, and the limit of the function p2x, it must tend to infinity to apply this result.